Let the recording start, then I'll start. Fine. Okay. So, welcome to this next session, lecture number 44 as such. So, in this session, we will be discussing variable DC link inverter. That is, we have gone through two main different types of inverters. That is voltage source inverters and current source inverters. We have seen that the working and operation of voltage source inverters and current source inverters. Voltage source inverters are those if your input to the inverter is a voltage type. Okay, so if the source what you are connecting to the inverter is a voltage source, then it is voltage source inverter. And according to the previous session, what I had discussed was current source inverters. There is no current source as such. There will be no current source as such, but using voltage source, if you are connecting, say, some large inductor in series with your DC source, then there will be a constant current generated, so that current will be used as input to the inverter. So those type of inverters are called current source inverters. So the say in those type, like mainly in the voltage source inverter type, we saw there that the output voltage of the inverter was like we were able to control the output voltage. What's the output voltage from an inverter? It is AC signal, right? So we were able to control the output voltage from that inverter, that is voltage source inverter, by varying the pulse, that is width of the pulses, right? So we have already discussed that, and I would recommend you to please go through and understand those sessions and then come back to this part. Okay, so there we varied the width of the pulse, which was used to turn on our switches or the semiconductor devices. So varying the width, we were able to control the output voltage in voltage source inverters, right? So that was what we called it as voltage control, right? And in that type of inverter output, we observed that there were harmonics, right? So the output of the voltage source inverter or the current source as such, it was a square wave, or sometimes it was a quasi square wave. So in that, the output had harmonics in that. So if you had to get a perfect sinusoidal output, means you had to go for say filter circuits, right? So if at all I have a circuit where I have constant pulse width, okay, and I'm using that pulse width modulation technique to vary the output of inverter, then this technique is nothing but using a variable DC link inverter. I'll elaborate on that. So if the pulse width are kept constant, okay, and you are using this to eliminate or reduce certain harmonics at the output voltage by controlling or varying the level of the DC input voltage, okay, by varying the amplitude or magnitude of these pulses. Okay, such arrangement is called variable DC link inverter. All right. So that is what we will be discussing today. So by the end of this session, you will be able to describe the variable DC link inverters. So before moving on to that, let us just observe mainly the difference between the voltage source inverters and current source inverters. So as I just briefed here, a voltage source inverter is fed from the DC voltage source, yeah, having small or negligible impedance, whereas current source inverter is fed with adjustable current, right? Adjustable current from a DC voltage source of high impedance, okay? So obviously the input voltage in VSI is maintained constant, that is voltage is maintained constant. In CSI the current is constant, but it is adjustable depending on the magnitude or the range of the inductor what you are using in series with the DC voltage source. In VSI, output voltage does not depend on the load, whereas in CSI, the amplitude of the output current is dependent on the load, right? In VSI, the waveform of the load current as well as its magnitude depends upon the nature of the load impedance, obviously, whereas in current, that is CSI, the nature, the magnitude of the output voltage and its waveform depends on the nature of the load impedance. VSI requires feedback diodes. If you can recall the circuit there, the voltage source inverters requires feedback diodes, whereas CSI circuits does not need a feedback diode. Here in VSI, the commutation circuit means what? To turn off the power semiconductor devices, right? Like power BJTs, power MOSFETs, IGBT, GTO. So here the commutation circuit is complicated because of the different range of voltages. The semiconductor devices also should be adjustable for different range of voltage, and to turn off them you need separate commutation circuit. So that's why it is complicated here. Whereas in CSI, we don't use these semiconductor devices at all, switches. Mainly the capacitors will be used. So the commutation circuit will be simple. So these are the main differences which you should be familiar with when you are talking about the two different types of inverters. So VSI and CSI, that is voltage source inverters and current source inverters. So moving on to voltage source inverter with variable DC link. So this is again, as I mentioned, variable DC link inverter. It's a type of inverter which works on, again, the principle that is, it is a type of voltage source inverter because the input is a voltage source. If the DC input voltage to the inverter is controlled to adjust the output, then we call such inverters as variable DC link inverters. Okay, so here as you can observe from the figure here, okay, as you can observe from the figure here, this is your inverter circuit and this part is your input. So the input to the inverter is a fixed DC source, right? So if you want to vary the level of the DC input, so that you control the output voltage, okay, output AC, output signal, then as I mentioned, according to the variable DC link inverter type, you need some circuit where you want to vary the or adjust the DC input level. All right. So for that, mainly a converter or a chopper circuit will be used. So this circuit, this symbol, what we have is a DC to DC converter, which is a chopper. And here, if you observe the symbol here, you should be familiar with the symbols as well. So here, the inverter symbol is, it converts DC to AC. So the symbol represents that. So DC to DC. So using choppers, we know we can either step down or step up. So depending on the type of the chopper, whether it is a buck chopper or a boost type of circuit, then you can vary the levels of the DC input. So, obviously in between these two circuits, the chopper circuit and the inverter, there will be a capacitor which will be feeding the regulated or the adjusted input, DC input, to the inverter. Okay, So this is a basic principle here, as you can see. So a DC link voltage by DC to DC converter or the controller rectifier circuit will be used here to generate the square wave output, as obviously. And if you want to adjust the frequency, then you have to go for adjusting the amplitude. So, okay, let me go back to 1 second. I have to stop sharing this and move on to give me a moment. Now I have to share. Okay. Okay, so yeah, so now moving on to today's topic in detail. Okay, so as I mentioned, the output voltage of an inverter can be controlled by varying the width of the pulses and to maintain the DC input voltage constant. So this is voltage control type, right? So a range of harmonics would be present in the output of this type of control where you have voltage control. So the pulse widths can be maintained fixed to eliminate or reduce certain harmonics, and the output voltage can be controlled by varying the level of input voltage. Such arrangement, as I just now explained, is known as variable DC link inverter. So the best circuit what you can have here for understanding variable DC link inverter is boost inverter. Okay, so if you recall the single phase voltage source inverter, it uses the buck topology, that is step down circuit, where the average output voltage was always lower than the input DC voltage, right? So if an output voltage higher than the input voltage is required, then obviously we have to go for a boost type of DC to DC converter, right? So which has to be connected obviously between the DC source and inverter. So in the full bridge inverter network, what we had observed previously in previous session, so if we are using the full bridge circuit as boost inverter to generate the output voltage higher than the input voltage, the basic principle that can be used is this. So using the full bridge network, if you are arranging your full bridge network in such a way that you are using two converters, say converter A and converter B, okay? So the circuit arrangement should be set in such a way that the output of converter A and converter B will be, they will be giving a output wherein the output of two converters, it will be a DC bias sine wave output, such that each source will only produce a unipolar output, as I have shown here in the right hand side. So which will be 180 degree out of phase. I'll repeat, the converters here should be designed in such a way that they will be producing DC bias sine wave as shown here, okay, such that they will be producing only unipolar output. So the output of both the converters, converter A and converter B, will be a 180 degree out of phase. Okay, so why is that, we will discuss now. So consider the two DC converters feeding a resistive load is as shown here, as shown in the circuit here with the with a generalized block diagram here. So the two converters produce DC bias sine wave output such that each source only produces a unipolar voltage. Okay. So the output voltage of the converters are described as, say, if you are considering VA is your output of converter A, then you can write it as DC plus Vm sin omega t, right? And if VB is your output of converter B, then if you say you are getting output VDC plus Vm sin omega t because of the output what we have discussed just now. Okay, so it gives a DC bias sine wave output, which means the level would be VDC and the output what you are getting will be 180 degrees, but a DC bias sine wave, right? So the VA, the output of converter A and converter B, you can take it as VDC plus Vm sin omega t and VDC plus sin omega t. So the output voltage is sinusoidal, which can be given as VA minus VB, right? So you will be getting 2Vm sin omega t. So using this basic principle, we can understand the variable DC link inverter, that is boost inverter. Okay. So the boost inverter circuit with two boost converters is shown here. This is your boost inverter circuit with two boost converters. I hope you are able to identify two boost converters here. So this part will be converter 1 or converter A. This part will, okay. This part will, oh, I cannot. Oh, 1 minute. This part will be converter B. I hope you are able to identify that. Okay. And here is your output. R is your output where you are observing V naught, and this is your input V in. Okay. So the rest of the circuit, it is nothing but the circuit designed in such a way you are getting a boost converter. The circuit is designed in such a way that is you have two converters based on this principle, basic principle. I hope you are able to understand that. All right. So the output of the inverter can be controlled by one of the two methods. One is, say, use duty cycle K for converter A and duty cycle 1 minus K for converter B. Yeah, K is nothing but what? Duty cycle, right? Which is given by turn on time period by the total time period, right? I hope you are able to recall things. So one of the methods to control these converters is, say, use duty cycle K for converter A and 1 minus A for converter B, or other method is use different duty cycle for each converter. Okay, let us observe how it works for a different duty cycle for each converter. So the circuit operation can be explained by considering one converter here, just to simplify things. Say consider only one converter, okay, this part, and observe the working of it. Okay, so this circuit is the equivalent circuit of converter A. I will give you some time to understand this circuit. Would you like to take down this circuit? Take this circuit down first. So if you know this circuit, then you will understand the working of equivalent circuit. Are you with me? Are you with me? Yes. Yeah, okay, thank you. So the equivalent circuit would be like this. There is some rearrangement taking place there. I want you to understand that. Only then you will be able to understand the working of the circuit. So quickly you take down the circuit here. And let me know when you are done. So S1, S2, S3, S4 are the transistors which are, okay, here again, I missed the arrow mark here. And D1, D2, D3, D4 are the feedback diodes. L1 and L2, the inductors, which are connected in series with the source, and capacitor C1 and C2 provides constant input. Are you done? Should I go to the equivalent circuit? Can I move on to see equivalent circuit? Okay. Now observe the equivalent circuit here, the rearrangement of the circuit. Note the changes there and the rearrangement where you are considering only converter A. If only converter A is used, and the operation of the inverter is explained using the equivalent circuit of converter A. All right, let me move on. So there are two modes of operation here, mode 1 and mode 2. In mode 1, observe here, when the switch S1 is closed and S2 is open. That means switch S1 is on and S2 is off. So the current, inductor current IL1 rises linearly. If you can observe the equivalent circuit here, diode D2 will be reverse biased because S2 is off, and the capacitor C1 will be supplying energy to the load. Observe the circuit. And obviously the voltage VA, the output of converter A, will decrease. Are you able to note the working of the circuit here? I will come to the equivalent circuit. Observe the equivalent circuit. When S1 is on, when S1 is closed and S2 is open. When S1 is on and S2 is off. So observe that. This will be shorted when S1 is on, S2 is open, this path will be open circuit, right? So D2 will be reverse bias because L1 will be, yeah. So here the current path will be in this direction. So IL1 will be linearly increasing, that is inductor will be storing the energy. Yeah, the potential at this point will be negative compared to this, so which will be reverse biasing the diode D2, right? So the current path will be this. So the circuit, you can observe the circuit here for mode 1, okay? And observe the output. What you can observe here, it is provided by the capacitor, right? So capacitor will be supplying energy to the load when in the condition S1 is on and S2 is off. Okay, this is only for converter 1, converter A, what we are discussing. So in mode 2, when switch S1 is open and S2 is closed, that is S1 is off and S2 is on. Now the inductor current will flow through the capacitor because of the connection there and the load as well. Okay, the current IL1 will decrease while the capacitor will get recharged. So this will be the circuit. I'll go back to the equivalent circuit. Observe that when S1 is off and S2 is on, observe the circuit and visualize how the circuit will be. When S2 is on means this will be shorted. When S1 is off, so this will be open circuit. So the path will be like this. So the diode D2 will be conducting. So the connection will be L2 will be getting connected here, right? This will be the path. So that is the equivalent circuit shown here, right? So the average output voltage of the converter A, which operates under the boost mode, can be found from, so if say converter A is operating in boost mode, we know the output of the boost circuit, that the average output voltage V8 is given by Vs by 1 minus K. Assume that the converter B is operating as or under buck mode. Okay, we know the output of the buck chopper or the step down chopper. So the average output voltage VB will be given by K into Vs, if you can recall things. Okay, then the average output voltage of the complete inverter, the whole inverter, will be VA minus VB. That is converter A, output of converter A minus converter B, right? So which will be Vs by 1 minus K minus KVS. This should be Vs, right? So obviously, which will be giving the DC gain of the boost inverter. Gain of the boost inverter, we know that it is given by output by input. So I'll go back to the circuit. So this is your boost inverter with two boost converters. Okay, so if you are controlling the two converters, two boost converters operating in two different modes, say one is operating as in a boost mode and the other in the buck mode. That means what? One, you are using it to step up your voltage level, DC input voltage level, and the other you are using it to step down the input DC level. Okay, so the output, what you will be observing at the output of the inverter will be the difference of the two converters, VA minus VB, which will be obviously giving the gain of the boost inverter. So this is the basic principle of variable DC link inverter. Go through the circuit. If you have any clarification at in any stage, we can have a discussion. Let me call upon someone to summarize points. Yeah. So immediately Anil Nair left. Okay, let me check B section. Yeah, Adeline Pinto, can you summarize what did you understand with variable DC link inverter?
Yes, ma'am. Initially, we have two converters, converter A and converter B, wherein the converter A is a chopper, which is a variable DC output, and we have an inverter, wherein the DC is converted into AC. Usually a switch wherein which is turned on and turned off.
My question, 1 minute, Adeline. My question is, Just tell me the basic principle of variable DC link inverter. What is the method you are using here? You need not explain me the boost inverter circuit. I want what is variable DC link inverter?
In which the DC input is converted into a fixed DC input is converted into a variable output DC voltage.
Correct, exactly correct. Why is it so? Correct. You are varying the input level. Exactly correct. Why? Why do you need to vary the DC input level? Why are you doing so?
To step up and step down the voltages.
Exactly, but why? Why are you stepping up or stepping down your DC input level? What you're answering is exactly correct. Next question is why? Why are we doing that? Let me give you a hint to answer that. In voltage source inverter type, okay, to control the output voltage, what we did, we varied the width of the pulse to control the output voltage. Okay,
Yes.
does that lead you to answer my question?
Uh, Based on that waveform, it gets shifted towards like to a particular.
Okay, you are not getting the point. In voltage source inverters, in voltage control method, okay, in voltage control method, what are we doing? If we want to vary the output voltage, okay, AC output voltage from the inverter, what we used to do? We used to vary the width of the pulses, okay, width of the pulses that were triggering your semiconductor devices or the switches, right?
Yes.
By
Yes.
varying the width, we were able to control the output voltage. So in this variable DC link inverter method, what are we doing?
Mm, Not sure, ma'am.
In variable DC link inverter, you have already answered. Maybe you are not able to relate it clearly. In variable DC link inverter, we are varying the level of the DC input, that's all.
The shifting, like
Varying the DC level means what? By
yeah,
stepping up or stepping
yeah,
down. You have already answered, right? So in variable DC link inverter, to control the output, thank you, Adlin.
yes,
To control the output voltage, we are varying the level of the DC input signal, okay, by keeping the width of the pulses constant. Now you have to visualize things here. The waveform I have not shown here. The in the other method, in voltage control method, we used to vary the width of the pulses to control the output voltage. In variable DC link inverter method, to control the output voltage, we are varying the level of the pulses, varying the amplitude of the pulses, keeping width of the pulse constant. Okay, so how do we do that? How do we vary the amplitude or the magnitude of the pulse? By using these choppers where we can step up or step down the level of the DC input voltage. I hope I'm able to convince you guys. Okay, so just go through, I will share the material there in Canvas, go through. If you have any queries, you can always get back to me. Okay, one more thing I want to, let me share so, all right. So there is assignment 4 coming up, wherein I want you to answer 5 questions. You have 5 questions in assignment 4. The submission date will be 14th. Okay, uh, let me share that. Assignment, yeah. So there are 5 questions. You need to answer all the 5 questions. The submission date of the assignment will be 14th. If you have anything to say with regards to that, you can. Yeah, this is for B section. B section only 15 are there. Okay. Yeah. So these 5 questions you will answer and submit by 14th of this month. So that will be your assignment. Anything to ask? Shall we